We're having some slight technical difficulties with the computer constantly making the disconnect sound, but hopefully that fixes itself because I don't know what's disconnecting because it doesn't look like anything is. Is my audio cutting out? If not, then we're good. Nope, okay, then we're good. So this is the Calc 2 hybrid session. Someone asked for examples from 11.6. So I'm going to start with that until more people come in, but we can at least cover some topics. Yeah, I have no idea what's disconnecting. Nothing looks loose and it's not like I'm moving a whole lot. So I'm just getting to 11.6 right now in the book. Yeah, you guys are in series and sequences, absolute convergence, and the ratio and root tests. Ooh. All right. Okay. So you guys covered absolute convergence. That's something that I haven't seen before necessarily. So, all right. Wait, did you guys actually cover absolute convergence? I don't think so. Okay. Yeah, it didn't ring a bell for me, and I've been working this job for 3 years, so I figured I should ask in case the curriculum changed. All right. So we can go over some ratio tests. Oh, this is just, yeah. Okay. All right. So simply put, ratio test. So that's going to be like the main subject of this ratio test. Is showing that for a series, a sub n, proving that this has a limit. So what we do is we find, so is convergent. So the way that we check this is the ratio test, and that's simply, so the equation is very easily written. It's just a sub n plus 1 over a sub n, but it never looks that nice typically. So an example would be, let me look up one real quick. So let's say, so example 5. So example 5 in 11.6. So if you go to your book, oh, example 5 and 11.6. You'll see test the convergence for the series, and then it's n to the n over n factorial. All right. So for this, so this is n equals 1 at the start to infinity. We need to check if it converges. So we're going to use this formula right here. So a sub n plus 1 and a sub n. So what we do is on the top, we put this equation, but every n we replace with n plus 1. So we have n plus 1 to the n plus 1 all over n plus 1 factorial. And then that's just the top, and then the bottom is just the same as you have here. So pretty easy to write the bottom. So I like to write my fractions on top of each other. I don't blame other people for not liking that. What you can do is, so you can either say, okay, you multiply these together. This is the method that I was taught when I was younger for fractions, but another method would be moving this up top but doing, so we're going to have n plus 1 to the n plus 1 over n plus 1 factorial times, and now we flip this, so it's n factorial over n to the n. This is just going to be what you do for most of these right away. And then the next step comes simplifying. So immediately you want to look for anything that's similar, and you'll see n plus 1 factorial and n factorial. Always look for those. So since we have n factorial will be, so n factorial is equal to n times n minus 1 times n minus 2 times yada, 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 times 1. So we just go down to 1. So this, so n plus 1 factorial will equal n plus 1 times n minus 1 times yada, 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 times 1. So we'll notice that we have all of this right here, and we just leave this out. So what ends up happening is we have, so n plus 1 factorial on the bottom, n factorial on top. This cancels, the factorial cancels, and we're just left with n plus 1. Now that we have n plus 1, we have n plus 1 to the n plus 1 over n plus 1. So this is to the first power, so we can subtract one of those, and now we're left with n plus 1 to the n over n to the n. So we have the same power. So in the end, we have the ratio test. So a sub n plus 1 over a sub n is equal to n plus 1 over n all to the n. And now we test the limit. So the limit as n approaches infinity for n plus 1 over n to the n. And so as we get larger and larger, this 1 becomes insignificant. So we can effectively cancel that out. And then we have n over n. N over n is equal to 1. 1 to the n is always going to equal 1. Now, here comes the tricky part, proving that it's convergent. And that's because, so since, wait, how did they do this? Did I do this wrong? Wait, oh, that's weird. They have a weird proof. So they have, okay, I'm just looking through the notes. So they have this, instead of just immediately canceling out, they have a weird rule. We have 1 plus 1 over n, which is common because we just split this fraction up into n over n plus 1 over n. We get this to the n power. And apparently, as n approaches infinity, this, so this equals e for a sum. But I don't really believe that. Well, it doesn't, so this is true. This ain't true. Reason being, oh wait, no, maybe that is true. Oh. Maybe this is e, huh? Did you know this? Sorry guys, a little technical, not technical difficulty. Have you seen that rule before? I was going to say this was divergent either way. Have you ever seen that rule before?
Let's see, that goes to 0, and then that'd be 1 to infinity.
Yeah, that's what I thought. Well, I think it's because it's not 0 and you're powering it an infinite number of times. So I guess, well, either way, so with our two methods, you either get 1 or e for your ratio. And this is, so every number past a certain point is going to reach a ratio between the last number of either 1 or e. If it's e, it's just going to grow a lot faster. If it's 1, then it's not necessarily growing, but if you add an infinite number of the same number, it's going to become infinite. So we know that this diverges. And that's because, so if we say R is the ratio, and that's because R is not less than 1. Because if it's 1, then it's equal to 1. If it's E, it's greater than 1. So we know that it diverges in this case. I don't know if you need to know this. If your teacher did not go over this rule, you don't need to know it. I guess I just picked a bad example. So let's try another example.
It's from that.
It's from that, which is all the way back in chapter 6. Okay. So let's go to another example. Let's say we have the series. Oh, wait, this is, did you guys do the root test? You did the multiply by 1 over n in class? Okay. Did you guys ever do a root or the root test? I don't know if that's part of the curriculum. I don't think it was either. I don't remember helping with the root test ever. No. Don't think so, not yet anyway. Okay, then you probably didn't go over it because I'm pretty sure the main test we use is the ratio test. All right, so let's do an example in the homework. So I'm on page 783. So this is kind of hard to show. So let's do let's do 15. All right. So 15 is going to be, I'm gonna use a new page for this. So 11.6. Problem 15. From 15, we have the series from n equals 1 to infinity of n pi to the n all over -3 n minus 1. So this is quantity, and that's important because we'll know that it's oscillating. So what we do is we do our ratio. So R is going to be equal to the limit as n approaches infinity. I'm just writing this all out now. And then we do n plus 1. So n plus 1 pi to the n plus 1 over -3 to the n. And then we multiply by the reciprocal. It's easier to write it out for most of you probably. Don't forget parentheses around there. -3 to the n minus 1 over n pi to the n. So right away, we have pi to the n plus 1. Pi to the n cancels. We're left with just pi on top. And then here we have n plus 1 over n, so we can simplify that. And then we have negative 3n, or so negative 3n minus 1 over negative 3n. So negative 3n cancels, and we're left with, so negative 3 to the negative first. So that means that we have, oh, I guess I could have also just left the negative 3 on the bottom. Well, yeah. So what we do is we combine. So we have lim as n approaches infinity of n plus 1 over n. Now this isn't to the nth power, so we're good here. So that's combining that. I'm just going to put those together. And then we have pi over negative 3. And that's because this is negative 3 to the negative first, so it moves to the bottom. Now you'll notice that we have a pi on top and negative 3 on the bottom. So instead of rounding pi to 3, we have to realize that it's 3.14 dot dot dot. I can't be bothered to write more than that. And we right away see that it's greater than 3. So we know that since, so as n approaches infinity, this is infinity over infinity, cancels to 1. And then we have 3.14 over 3, which is also greater than 1. And since it's a negative, we have to know that the radius of convergence is going to be, so negative 1. And you'll notice that I have a greater than or equal to negative 1. Reason being is if it approaches negative 1, because it's oscillating. So it'd have add, subtract, it averages out to 0. So we don't, or so we can include negative 1, we still check. But yeah, so from there we know that since this is going to be less than negative 1, so it's going to be like negative 1 point something, it does not converge, so it diverges again. Any questions about that? If not, I'm willing to answer any question that comes up. If you've thought of something, if you have some homework problem that you want to go over, if you want more examples of this, I'm down for whatever. No questions? Can go over another one of these. I'm just trying to figure out the good one, maybe one that converges this time. Yeah, let's just do problem 7, real simple one. So problem 7, again, 11.6. So 7.6 problem 7, we have the summation of n over 5 to the n. So what we do is we solve for r. R is the limit as n approaches infinity of n plus 1 over 5 to the n plus 1 times 5 to the n over n. So immediately we see 5 to the n over 5 to the n plus 1. 5 to the n cancels. We're left with 5 on the bottom. And then we have this is equal to limit n approaches infinity of n plus 1 over n. This cancels to be 1 as n approaches infinity. And then we just have times 1 over 5. And so since we have 1/5, so r equals 1/5, which is less than 1. And since it's less than 1, we know that this converges. So when you have a real simple one like this with not too many terms, it can become pretty straightforward in the simplification. Trick is just getting this process down, write out your series, write out the ratio. So do n plus 1 as the fraction normally, because most of these are going to be fractions. I don't think there's any examples that aren't fractions. So you do replace n with n plus 1, put it there, and then put this exact same thing, but inverse, or well, reciprocal is the correct term here. Put the reciprocal down, multiply, cancel, simplify, and you're done. Any other questions? If you guys could come up with examples, that'd be great, because I don't exactly know what you guys might be struggling with. It always helps if we have more people too, but we're here for another 40, kind of 30 minutes so that we can swap. Do you guys have homework due this week? Looking at what was signed right now. Okay. Now I think about it, I probably could pin this, and that would probably help. I don't think of pinning that earlier. I hope people can actually see. Yeah. I was just confused because my screen was not the one that was showing. So I was like, huh. Where did I put the? Just kind of putting this here. So for people that are looking at the recording, if they couldn't see it before, that they at least have this. So up to heavy session. And that's it. So now people looking at it can just pause and see my work. Hopefully they understand. Oh, we lost one. Sad days. Let me shoot ready. not many people have been showing up since break. Oh, there's a true false question that says the series from n equals 0 to infinity of n o or so n over 2 to the n. Is that parentheses around the n over 2? Yeah. Close the cap on this. All right, so we have so n equals 0. Oh, it's 2 to the, oh, okay, yeah, 2 to the n. Okay, that makes sense. All right, so we have infinity, n equals 0, and then n over 2 to the n. All right. So for this, we're checking if it converges or diverges. So we're saying, so true or false, this series diverges. So best way, ratio test. Always do ratio tests. It's just a nice and easy way to confirm whether it diverges or converges. So we have n plus 1 over 2 to the n plus 1 times 2 to the n over n. So here, kind of just like the problem that we did on the homework doing problem 7, just this is now a 2 instead of a 5. All we do is we say, okay, 2 to the n cancels with that, so we're just left with 2. And then we have n and n plus 1, so we have equals n plus 1 over n, I forgot to write the limit, times 1/2. So this, since it's the limit as n approaches infinity, this cancels to be 1. So now we have r is equal to 1/2, which of course is less than 1. So we know that it converges. So does it diverge? No, it converges. So we know that it's false. A ratio test is a nice and simple way to test it. The only time where you have to worry is if the ratio is equal to 1 or -1. Typically -1, it's going to converge, but there are some cases where it doesn't. And mostly the cases where it doesn't is kind of like a sine thing where there is no limit technically because it oscillates. So if you have, oh, what would it be? Well, I guess one of the easiest things is if you just had, so this would be an example of a -1. Oh, a lot to write out. Are you comfortable with sharing your screen so I can copy it then? Okay. I think you guys should be able to share screen. I don't know. Yeah, all participants can. Okay. Oh yeah, that's a definition. So that's actually part of the absolute convergence. So you don't have to worry about the absolute value there, because think of it, so I wrote this down earlier. We have R, or so that's not true. It can't be that. Well, sometimes it can. It's weird. Actually, no, can never. I don't think it can ever converge if r equals 1. So we have so if you have the sum of a sub n, so this is literally the definition. So this converges. This is the definition of kind of the ratio test in a way. If ln as n approaches infinity and an absolute value a sub n plus 1 over a sub n is less than 1. And that's because it would be within these bounds. So yeah, we don't have to, so that's more of a, just a definition. And in the book, you would find that should be true. Because the way that you solve with absolute values is you'd say, so since it's the absolute value, that means that it would be equal to plus or minus 1. But since it's a inequality and it has to be less than 1, it has to be in between -1 and 1. And so keep in mind, I just put this equal to because oftentimes if it's -1, it is going to converge. The only case where it won't is if you have some constant, like let's say we have 5 times -1 to the n. All right. If we do this, so the series would be, so let's say we start at negative or n equals 0. So n equals 0, this is 1. So we have 5, then we subtract 5, then we add 5, subtract 5, add 5, subtract 5, ... You get the point? Well, if we go, so the sum right here is 5. Sum here is 0. Then we're back to 5, 0, 5, 0. And so the ratio between each of these terms is -1. But because it never was decreasing, what we know is that we're just adding and subtracting the same thing over. And so our sum oscillates between there, and there is no limit. So we say that this wouldn't converge. And I don't remember if we necessarily say it or says it diverges. We might. Yeah. Depending on how the problem is laid out, it will vary, but for the most part, you say it doesn't converge because it doesn't. So yeah. Any other questions? You at least made it through half of the hour. That's better than some days. At least last semester, I had some days where I just didn't have anybody. Thinking good, thank you. All right, well. I don't know if anybody's gonna come by. Most people don't come by in the middle of this, because it's more designed as a help session throughout the hour rather than our walk-ins, which will also be starting up soon, but that's also for general classes. You get more specialized help in these, which is good. All right. I guess I'll pause recording for now. Yeah. I'm gonna pause the recording then.